So it's a wonderful pleasure to be speaking at this seminar again. Actually, almost exactly 2 years ago, I think I gave a talk at this seminar series about some work that was sort of ongoing. We're in the middle of a wonderful period of confusion relating two subjects that seem at first to have absolutely nothing to do with each other. A very basic question in physics having to do with calculating scattering probabilities for scattering processes, or more precisely, scattering amplitudes for particles like gluons, which are an important constituent of the proton, quarks and gluons. So scattering amplitudes of quarks and gluons on the one hand, and a structure that we had sort of stumbled into in the Grassmannian on the other hand. And as a result of that seminar, we had a number of months of absolutely wonderful interactions with Bob and Mark and Pierre that clarified things an enormous amount for us, and also eventually put us in contact with some relatively recent mathematical literature where the same structure occurred. And the structure is known as the positive Grassmannian, and we spent quite a bit of time after that working together actually with two mathematicians, Sasha Goncharov and Sasha Posnikov, to really fully make the connection. And there's a whole story there. We had a paper that came out in December establishing many of these connections, which we're very, very happy about it, and would not have happened without the beginning at this seminar, I don't think. But there's also something, this has been part of, at least for me, about a 4-year program to try to reformulate quantum field theory from the start, eschewing and discarding the usual notions of space-time, Hilbert space, locality, unitarity, all of the normal foundations of field theory. They're correct. Of course, there's nothing wrong with them. They're exactly correct. But it's become clear over the last 10, 20 years that holding fast to these principles and making them completely manifest in your calculations is obscuring aspects of the answer. That there are properties of the actual physical observables that are hidden when we demand this strict adherence to the obvious rules that we're handed. And so it seemed very likely, or at least that's the program, to try to find some way of recasting, just not doing new physics, not doing anything speculative, but just trying to recast ordinary quantum field theory, at least to begin with, for the answer to certain physical processes like scattering processes, using some kind of new ideas, some new mathematical structure, something which does not highlight or make obvious, at least to begin with, the ideas of locality and unitarity, but has them as outputs, and instead makes other things more obvious, makes other properties of the answer, and, well, things that I'll say in a little more detail, a little more manifest. And so, anyway, the sort of step 0 of this program is to try to accomplish it for the very, very simplest example of a non-trivial quantum field theory that we know in 4 dimensions, which is the maximally supersymmetric gauge theory. In, furthermore, a particular limit of an infinite number of colors where the only diagrams that you draw are planar diagrams. If you're drawing Feynman diagrams, you'd only look at planar diagrams. So this is a healthy, interacting, beautiful quantum field theory. It's been enormously important in theoretical physics for the last 20, 30 years. And even in this limit, it's of course local and it's unitary. And so there's a challenge to try to recast the question for scattering processes in a different way. So that's sort of step 0 of the program. And all the developments that I was telling you about a second ago relating scattering amplitudes to the positive Grassmannian were, stepping towards even that step 0 goal, but not quite getting there. There was always a sort of a cord tying us back to the usual way of thinking about things. I'll be a little more precise in a second. But what we've seen now in the past number of months, and this is, I should say, work with my student Yaroslav Tarenko, who's in the audience here, is we've cut the cord. So I think we have an ab initio definition of what this object is. I could, since you're mathematicians, I could just write it down on this board, and we could spend the rest of the lecture analyzing its properties. But since I'm a physicist, I won't do it that way. And I'll maybe write it down at the end of the lecture on that board what it is. But as you'll see, it's some formulation for what the physics is where absolutely none of the usual things make an appearance. There's no Lagrangian, there's no gauge symmetry, there's no path integral. There's nothing even that roughly resembles Feynman diagrams, which is always still something that we had in our previous picture. They weren't really Feynman diagrams, but it had the width and the smell of something that came from its field theory origins. And a little more precisely, the positive Grassmannian is a nice part of the Grassmannian. It has a cell decomposition. And there was a correspondence between cells of a given dimensionality of the positive Grassmannian and certain building blocks from which you could build the whole scattering amplitude. And understanding that correspondence was wonderful, and this is what this work that I mentioned earlier was about. But at the very end, you had to put these building blocks together in a specific way to get the actual physical answer. And what the rules were for building together in that particular way, we didn't understand other than by appealing to what we were told to do by quantum field theory, by the usual way of, well, at least something derived from the usual way of thinking about field theory. And so that's something that was the sort of last vestige of the connection. And that's the thing which we no longer have to do. So as I said, I can write down on that board an ab initio definition of what the object is. But let me build up to it. And I should also say I spent, I think, 3.5 hours giving lectures like this to my physics colleagues a couple of weeks ago. So I will certainly not be able to really explain both the physics and the mathematics properly in the time I have today. So what I think I will try to do is, just spend a few minutes at the start telling you some impressionistic things about the physics, but then tell you what the mathematical structure is. It's very sharp, it's very simple, and as far as I can tell, while the previous story ended up being connected to the positive Grassmannian, which is a known object to mathematicians, these objects, as far as we know, are not known to mathematicians. So there's really something new, and I think we could sure use a lot of help in understanding their structure, what they do. As you'll see, we've really reduced the problem of calculating amplitudes to finding a cell decomposition of some nice space. So it's really triangulating something. And we have some intuition for how the triangulation works, but there's surely more powerful ways of thinking about it. So that's what I'd like to tell you what the space is, at least motivate why it's interesting, show you why just its mathematical properties reflect aspects of the physics, deep aspects of the physics, and then at least state what some of the open questions are. All right, so just by a little bit more of a concrete introduction, normally when we think about calculating scattering processes, so let's say those particles are gluons, we'll imagine all the particles here are massless. We imagine drawing pictures like this that Feynman told us how to draw already 60 years ago. So you have some particles in, some particles out. We actually, by convention, imagine that all the particles are outgoing, let's say. So it's like a picture of the vacuum going to a bunch of particles out. And what we're supposed to do is just draw all the pictures of this sort that we can and add up all the different ways, and add up all the different diagrams. And this reflects the two big principles of 20th century physics. On the one hand, we have locality. The interactions take place at points in space-time. That makes it manifestly compatible with the laws of special relativity. On the other hand, it's quantum mechanical. So you have to add up all the different ways that the process could have happened, and so you get some final answer. Okay? And these calculations are actually important for practical to particle physicists questions. If you want to compute what happens when you collide protons at the Large Hadron Collider, well, you have to figure out what happens from just ordinary physical processes, just subtract it and look for new physics. And the sort of dominant thing that happens, if you have a proton here and a proton here, The proton is made out of quarks. And roughly speaking, the quarks are held together with gluons. And really, most of the time, what happens is that the underlying gluons collide with each other. So you can have 2 gluons in and 2 gluons out, for example. So that's an important process. You don't actually see the gluons coming out. You see a jet of strongly interacting particles coming out. But anyway, the fundamental first simplest process is 2 gluons in, 2 gluons out. And that's a process that we give students for textbook exercises. So, you add up 4 Feynman diagrams that look like that, and you get the answer. And that's something that you give them a few days to do, and you can actually do it. But for practical reasons, people needed to do slightly more complicated calculations. 2 gluons in, 3 gluons out. 2 gluons in, 4 gluons out. And there was just a combinatorial explosion of complexity. So 2 gluons in, 3 out is already 30 dense pages of algebra. You cannot possibly do it by hand. It's 30 dense pages of algebra. 2 to 4, which you even need to do, is 100 pages of algebra. Okay? It's just a horrendous nightmare. And you might think that it looks complicated because it is complicated. Yes?
Is it accidental that you're only drawing 3 diagrams?
Yes, yes. To begin with, I'm only talking about the lowest order diagrams that are just tree-like. Later, we'll also talk about diagrams that have loops in them and so on. But we're even talking about the leading simplest possible processes. Okay, so even the simplest possible processes explode very quickly. And you might think that it looks complicated because it is complicated. Not every question is guaranteed to have a simple answer. And part of our goal in theoretical physics is to define as interesting the questions that have simple answers. But so you might think that it's just complicated because it is complicated. But the astonishing thing that people discovered was that the answer was not complicated. In fact, in this case with 2 to 3, the 30 pages of algebra actually collapsed to a single term, 1 term. Okay? The 80 pages of algebra collapsed to 3 terms, and so on. Okay? So there's somehow tremendous redundancy in our description of this physics. The word redundancy is actually used judiciously. That's what the gauge redundancy is actually all about. When we just describe these particles of spin 1, we describe them as gauge theories. And the gauge redundancy that we give the theory is what allows it to manifest locality and unitarity at the same time. So that's what the Feynman diagrams are doing. They're making it totally clear that this process is compatible with relativity and quantum mechanics, but that comes at a heavy price. Okay? It's obscuring the fact that the final answer is 1 term and not 100 pages of algebra. Now, people discovered more things. People discovered that the answer actually has infinite dimensional symmetries that are totally hidden in the Feynman diagrams. You only see it when you finish doing the calculation, but you don't actually see it anywhere term by term. When that happens, when you have symmetries that are being obscured, then it really feels like that there should be some better way of thinking about it. But if I say this a little more, so we have this first way of thinking about things. This is really not only the first way, but it's the only way that works in complete generality for every theory. In a sense, it defines the perturbation expansion for amplitudes in any field theory as a summing over Feynman diagrams. And what this is making manifest is locality and unitarity. Okay. Now, actually, on the actual final answer, if we call this final amplitude, we just call it something. Depends on n extra particles. If someone just hands you a function of the external momenta, and it also depends on the helicities, the spins of the particles, or the spin in their direction of motion. They're all massless particles. So the helicities can be plus or minus 1. So there's this discrete label h, which is plus or minus 1 for each one of the external particles. So a runs from 1 to n. But if someone just hands you this function of external momenta and helicity, and says, there, that's what I think the amplitude is. There's a check you can do to see if they've fooled you or not. You can see if it's local and unitary. You can check whether it's local and unitary. And locality and unitarity mean something tells you something about the singularity structure of this object as a function of the external data. So you don't have to worry about the details, but I just want you to look at this impressionistic picture, because these pictures are what we're going to later see as geometric properties of this object in the Grassmannian that we're going to talk about in a little bit. But I just want you to get an idea for where these pictures are coming from. So for instance, if we just draw these tree-like graphs, the idea is that the only singularities that the amplitude can have occur if you take some subset of the external particles. So now, if we draw Feynman diagrams, we would have some momentum flowing through there. That would be the sum of all the momenta out here. And in general, all these momenta will be light-like. They'll all be null. So they'll all have the energy component equal in magnitude to the momentum component. But obviously, if you add up a bunch of them, they're not going to be null anymore, which is why in the usual language we talk about virtual particles all the time. This thing in the middle is not a real particle. It's not a real photon, let's say, or a real gluon. It's virtual. But if you happen to tune the external momenta such that the sum of these momenta does become null, then the amplitude needs to develop a pole. It has to develop a pole that goes like 1 over the sum of all these momenta on the left squared. And on that pole, so that's the first important point. The only poles that the object has, the only poles that it has, are of this form, the sum of the momenta squared. That's locality. It's very easy to write down functions that have other kinds of poles in them. Okay? These would simply not correspond to local processes in space-time. Okay? Things that look like 1 over p squared are really telling you there's some point-length interaction and some particle propagating over a long distance. And the singularity is occurring because the distance over which it's propagating is going to infinity. Sure, yes.
So, for example, I don't really understand what notion of locality you're using. I mean, this discussion could, for example, be done for a theory that violates the usual connection between spin and statistics, which we believe is not the local theory, but according to
all of that actually comes out. Because I'm not done yet. I've told you what locality is. I haven't told you what unitarity is. Okay? So locality is just this statement. Unitarity, even for these simple tree amplitudes, unitarity is a statement that the residue on that pole factorizes into these two pieces. Okay? So the residue looks like it factorizes into a left piece and a right piece. Okay? That's it. If you can hand me a function which has the properties, those are its only poles, and all the poles, it factors into lower point pieces, the last thing I have to tell you is that this process could go all the way down until you are left with the 3-particle amplitude. And the 3-particle amplitude turns out to be completely determined up to an overall constant just by symmetries, just by Lorentz symmetry and translations. Poincare symmetry entirely determines the structure of the 3-particle amplitude. So there's no choice there. So if you hand me something which factorizes properly, it's local and unitary, which means it has this kind of pole, and it factorizes properly, then that's the answer. That is actually the answer. Feynman diagrams are one way of guaranteeing that that's true. Okay? That make it manifest that that's true. But that's what at least at this lowest order, that's what this condition actually is. So we have to see this kind of structure. So let me write it schematically. That the singularities of the amplitude, which I'm suggestively writing as a boundary, break up into pieces that look like that. Okay? Now, I'm going to further specialize to
Let me
yeah.
just make sure I understand something. So is this a statement that's special for the supersymmetric
No,
theories?
this is completely general,
It doesn't
totally
really matter.
general.
I can look at any gauge
It can be
supersymmetric
gravity, gauge theory, any theory.
Okay.
In fact, if you just begin with this, I mean, this would be another talk, but you can just begin with the 3-point functions, which I told you are nailed by Poincare symmetry. You have no choice.
Yes.
And then just make an ansatz for the first non-trivial 4-point function. And you'll find that it's almost impossible to write down a 4-point function that satisfies these simple properties. In fact, it only works for a very tiny set of theories, which happen to be the theories that we see in the world. Particles of spin 0, 1/2, 1, 3/2, and 2. Well, we haven't seen 3/2 yet. But that's it. It's that you can't have particles of spin 17 halves. Not because of just from this trivial check already. It's an extremely powerful constraint. And you need both. It's both relativity and quantum mechanics. Both locality and unitarity are needed to just nail these structures. And things like spin statistics and so on are all an output. They're all an output in this way of thinking about things.
Three-point function
Yes.
determines the
That's right. Then the three-point function determines the physics. That's right. Okay. Now, I'm further going to be specializing to theories which are where the diagrams are planar. We're only going to draw planar diagrams. And so if they're only planar diagrams, then it's literally like this. There's no cross legs here. There's a cyclic ordering to the external labels. So there's a cyclic ordering 1, 2, up to n for the external labels. And so you further see that this factorization, this statement of locality, this property is called factorization, involves 4 special labels: I plus 1, j plus 1. Okay? So we have to have this. So something that the singularities involve I plus 1, j plus 1, and the object has got to split in this way. Now let me just tell you even a little bit more. I will then skip. So amplitudes are really functions of momenta and so on and so forth, but you can process it, and so they're much simpler functions. So in the simplest instance, the external data you can just think of as 4-dimensional vectors, okay, modulo and overall rescaling. So points in P3. So I'm a physicist, so I write my indices as explicitly as possible. So just points in P3. So the external data is just given by giving n points in P3. Okay? And the amplitude is just a function of homogeneity 0. So it's really just a function on P3. Okay? So we have some mn that depends on the z's, and this is equal to TAZA. There's actually one more piece of data that labels the amplitudes. It turns out that the number of these gluons that have negative helicity well, in what I'm doing here, it's -2, is an important quantity. So for general reasons, the amplitudes with all plus helicity vanish, all but one plus helicity vanish. So you begin, the first non-trivial case is where you have 2 negative helicity and the rest positive helicity. And if we're talking about these 3 amplitudes, even that case, which would be k equals 0 here, is trivial. M is 1. It's not 0, but it turns out to be 1. So life starts getting interesting when k is when k is bigger than when k is 3, 1, 2, and so on. Yeah.
P3, is that because you project by space-time?
Yes. So the correspondence is that. So let me tell you what the correspondence is. So we started off with particles having momenta, so this is actually useful. But because they are ordered, I can draw the momenta end to end on a 4-dimensional piece of paper, right? So let's call this first momentum P1, P2, and so on. Okay. Then it makes a closed polygon. Right? So momentum conservation is a statement that the sum of all these momenta add up to 0. So we have a closed polygon. So we can write each one of the p's as x. We can just label things by just giving the vertices of this polygon. Okay. Now this is 4-dimensional space, but we have the twistor or Klein correspondence between 4-dimensional space and lines in P3. Okay. So each one of these x's is some line in P3. But the important point is that these momenta are null, right? So 2 points being null separated in space-time means that the corresponding lines in P3 intersect. So we have a set of mutually intersecting one after the other lines in P3. And therefore, I can draw this picture in P3 just by giving the intersection points. Those are these z's. Okay? So if I hand you a bunch of z's in P3, I can build for you a bunch of x's back in Minkowski space such that adjacent guys are null separated from each other, which is exactly the data that we want. Okay? But this is a very important point because you see that the sum of a bunch of consecutive momenta, which is the only kind of object which occurs in those factorizations, is just something like xi minus xj squared. Right? So if I take this p plus that p plus that p, it's just x. It's that difference. So the poles here occur when xi minus xj squared goes to 0, which means geometrically when zi plus 1, zj plus 1 are coplanar in P3. Okay? Because the line I plus 1 should intersect the line jj plus 1. Okay? And so we can say this another way. So the poles occur when that goes to 0. Every time I write a bracket here, I'm just contracting things with the antisymmetric tensor. I'm taking the indeterminate. Okay?
Now, what are you doing there when you said it goes to 0?
So this is where the poles are. Okay? So the amplitude is a function of z's, and the poles happen when, in this funny situation, when I plus 1, jj plus 1 become coplanar, right? And on the pole, the object has got to factorize in this way. And if I'm actually a little bit more, if I state a little bit more detail, it has to have some factor that actually knows exactly where they go on the plane. Okay, so I mean, I can approach a plane in many ways. So there's some factor that knows how they go on the plane, and then the rest is just splitting into a left and a right. I plus 1, j plus 1. Okay. Now this is just tree amplitudes. These lowest.
What does
right.
this arrow mean? It goes to 0. What does that mean?
Well, this is a rational function. In the simplest case, this is a rational function of the z's.
Yes.
So it has poles.
Yes.
And the statement is that the only poles occur when I plus 1, jj plus 1 are coplanar. That's all. Those are the only poles. And I'm telling you also the residue of the pole. The residue of the pole has got to have breakup in this way, with a little extra factor that tells you precisely how they live on that plane. Okay. Now, so far I was only telling you about tree amplitudes. We also have these quantum corrections, or the loop amplitudes. And and so there's a more general story for what the singularity structure is. I won't dwell on this second point at length. I'll just draw the impressionistic picture. So if you're at L loops, what we're doing before is L equals 0. But if you're at L loops, there's one new piece which looks like the L minus 1 loop amplitude with two of the legs identified with each other. So these are the two kinds of singularities that the amplitude has. And as I said, at loop level, should have said this too. At loop level, the amplitude is it's the integral of it's an integral over some loop momentum variables. But those loop momentum variables are actually most easily thought of as just points in this x spacetime. So I have L points in the spacetime, and I'm supposed to integrate over them. So there's some form. There's some rational form, which is a function of these L extra points. And I'm supposed to integrate over it to get the amplitude. But we'll really be concerned with the form for most of this talk. I will say a little bit about the actual. I'll say a little about the integrals at the end. And so back in P3, each one of these is we just have a bunch of lines in P3. So we have L lines. At L loops, we have L lines in P3. So that's the data. The data is we give the z's for the external particles, and I have also in addition L lines in P3. And I have a rational function on this space, and its singularities have this property. Okay? And as I said, Feynman diagrams make this obvious. So this is just said in equations what locality and said more sharply in equations what locality and unitarity are. Okay. Now just it is possible to forget about the origin from Feynman diagrams, and just knowing that these are the singularities, you can, roughly speaking, use Cauchy's theorem to determine. So this is a rational function. You know what all of its poles are. So roughly speaking, you can use Cauchy's theorem to reconstruct it. Okay? And so it is possible. It's possible to do that. That. It has a name in the physics literature. It's called the BCFW recursion relations. It gives you a recursive way of building up higher point amplitudes from lower point ones. And exploring the properties of those objects was very, very important in all of these ideas, and in particular in establishing this connection to the positive Grassmannian that I talked about before. I haven't defined what the positive Grassmannian is yet, but I'll tell you what it is in a second. But roughly speaking, there was this recursive way of building up the amplitude that in the end expressed the amplitude as the sum of a whole bunch of terms. But in this recursion relation, you have to make choices everywhere. It's not, for example, cyclically invariant. You pick two particles to be special, you do some deformation, and off you go. But there was no one unique presentation of the answer. There was tons of different ways of presenting the answer. Of course, they all added up to the same thing. And it's some miraculous rational function identities that all these different presentations were actually the same. So that was a very rapid way of arriving at the answer. It also had an important physical characteristic that the individual terms that you got in building the answer up recursively could not be given a local interpretation. So they really weren't coming from ordinary space-time processes. And further thinking about the structure of those individual terms, put them in essentially one-to-one correspondence with the positive Grassmannian, or with the cells of the positive Grassmannian. But again, how you glued them together to get the answer was solving this equation, essentially. So it wasn't getting locality and unitarity out. It was using locality and unitarity to tell you how to glue these basic building blocks together. The building blocks is handed to us from the positive Grassmannian, if you like, to get the right answer. Okay? So what I'd like to do is actually tell you now what the actual object is that tells you to glue them that way to begin with. And then we can read it backwards and see that it does this, and see that locality and unitarity actually emerges from it. And as you'll see, in the simplest case, it's really a very natural extension of the positive Grassmannian. And there's a further extension of it, which is, I think, natural to motivate both physically and mathematically, that actually goes to the whole thing. So, but that's all I want to say about physics. And so all I want you to remember is those pictures impressionistically, and I hope you have a sense for where they come from and what they have to do with the physics. I should say that if you know, as a physicist, it seems very hard to imagine anything that would make those properties happen that wasn't the usual formulation of field theory. After all, we're saying that why do we have those singularities? It's because there's some particle there. It's a virtual particle, and it's becoming real. And it's very tied to this local and to this space-time picture for how all these things are happening. It's not a totally garden variety way an object breaks up into two, right? It's so that's what the real interest here is that I think the invariantly interesting thing about what I'm going to tell you is that there is really a totally different way of making that happen from a completely different kind of mathematical structure. Okay, so let's now start talking about the math. And so I want to start talking about a triangle. Okay? The venerable triangle. So imagine that we just have 3 points in Euclidean space. And I first want to talk about the inside of the triangle. So I have a triangle, and I want to talk about the inside of the triangle. Well, the easiest way to think about the inside of the triangle is to imagine that these points have masses C1, C2, and C3. I won't call them M. Okay? and that we're just looking at the center of mass of those 3 points. So the center of mass is somewhere inside the triangle, obviously. So let me denote that as C1, Z1 plus C2, Z2 plus C3, Z3 over C1 plus C2 plus C3. Okay, and as I range over all positive C's, so as all C's are positive, then I fill up the inside of that triangle. Now I can say this more naturally projectively, obviously. So if I have 3-dimensional vectors, Z1, 2, 3, and a 3-dimensional vector y, then all I'm saying is that y is equal to C1, Z1 plus C2, Z2 plus C3, Z3, where now the C's are only defined up to rescaling. So let me just write my explicit indices here. So I runs from 1 to 3, 3-dimensional vectors. And the C's are positive. All right. So that gives me the inside of a triangle. So that has the obvious generalization to a simplex. So I can have a C1 up to Cn mod GL1 with all the C's positive. Well, it's really all the ratios are positive, but let me just not keep saying ratios. I'll just declare that one of them is, that they're all positive. All right, and that's the inside of a simplex. Now, the positive Grassmannian is just the generalization of this idea to the Grassmannian. So we think of this as G1n. Well, we can think of GKN. We can think of GKN as k-planes in n dimensions at first. So that way we think of GKN, one way of thinking about it is just by giving the k vectors in n dimensions whose span gives me the k-plane. So it's a k by n matrix, which I'll write mod GLK, so that only the plane matters. So that's if we think about it horizontally. We can also think about it vertically as a bunch of column vectors, n column vectors. So these are just n points in CK mod GLK. Right? Those are the two ways of thinking about the positive Grassmannian. And so we'd like to mimic this idea now in the Grassmannian. And so we imagine that we have this k by n matrix C. So again, if I'm very explicit, alpha runs from 1 to k, a runs from 1 to n. But this is just C1 up to Cn. And the analog of all of these guys being positive is, well, it has to be a GLK invariant statement. So the analog is that all of the minors of this matrix are positive. But of course, the minors are antisymmetric, so I have to give an ordering. So I have to fix an ordering for the external particles, for the columns, sorry, for the labels. And I declare that these minors are positive if the A's are ordered. Okay? Now, naively, there's n factorial different positive Grassmannians for each different cyclic ordering. Sorry, so for each different ordering. But there's a cyclic symmetry under which C1 goes to C2, C2 goes to C3, and Cn goes to, it picks up this annoying minus sign. It's a twisted cyclic symmetry, a -1 to the k minus 1 C1. Okay? But up to that twisted cyclic symmetry, we really have, there's a positive Grassmannian for every cyclic ordering of the external columns. Okay. So this generalizes the notion of a simplex to the Grassmannian, and it's a very beautiful object. It has a much richer cell structure than a simplex, with the simple reason that there are, for the simplex to go to the boundaries, you just set the C's to 0. But here you can't just willy-nilly set any minor that you want to 0 because they satisfy quadratic relations between each other, the Plucker relations. Okay? So there's a long story, very beautiful story, worked out variously by many people over the past number of years for in the last decade for actually working out what all the cells of the positive Grassmannian look like. And there's a lovely story associated with it, associated with bipartite graphs. Those graphs have a physical interpretation, and so on and so forth. But I don't want to talk about that, because we can talk about the structure of the object I'm interested in without telling you in detail about what this thing looks like. If you actually want to go do computations and figure out actually how to do these cell decompositions that we'll be talking about in a moment, this stuff is crucial. You have to understand this positroid inside out, because as you'll see, they're the building blocks for the bigger object that we're interested in. But for just talking about what the object is, we don't have to do it. Okay, but anyway, this was one chain of generalization that started from a triangle, went to a simplex, and ended up with the positive Grassmannian. All right. But now I want to talk about a different generalization. The other obvious generalization, which is, let's look at the inside of a polygon. Instead of a triangle, let's go back to Euclidean space and talk about the inside of a polygon. Now, what I want to do is specify the vertices. Oh, sorry. Maybe I should have said one thing to those of you who aren't familiar with the positive Grassmannian, just to get some intuition for what this positivity property means. It's actually the first non-trivial case is G24 or G2n in general. For my purposes, and actually it's a little even easier to visualize if we go to G3n. Let's think about what positivity means for G3n. So in G3n, I have a bunch of three-dimensional vectors. Okay? So I can think of these as points in P2. I have a bunch of points in P2. And what does positivity mean? Positivity, saying that all the minors are positive, is nothing other than saying that these points make a convex polygon. Okay? So in this case, positivity and convexity are the same thing. Okay? So let's remember that. Okay. But now let's go back and think about not the triangle, but a polygon. And again, if I want to give the vertices of the polygon, if I want to talk about the inside, it won't make any sense. If the points are just randomly scattered, the inside makes no sense. So the points have got to be convexly, the vertices of a convex polygon. So the z's, so this is an important point, my external data, if you like, the z's, has got to be positive. In other words, ZA, these minors, are positive for A less than B less than C. Okay, so now I have a convex polygon. Now I want to talk about something else. I want to talk about the inside of this polygon. What is the inside of this polygon? Well, the inside is just the same as we did before. It's just C1, Z1, the same center of mass idea, plus Cn, Zn. Okay. A point on the inside is expressible in that way, where the C1 through Cn, again, are in G1n, and are positive. Okay. But note the little thing that we've done here. We're actually combining two different positive things in order to define the inside of the polygon. On the one hand, the external data is positive. The z's are positive. On the other hand, we're taking a positive combination of the positive external data. The c's are positive and the z's are positive. They're both positive. Okay? And that's the essential novelty relative to the positive Grassmannian, which was just about the c's being positive. Now we're combining both something about the c's and something about external data. These z's will eventually be the z's we were talking about before. Okay? So the z's that specify the external data. Okay. All right, so actually let's just do the first generalization of this away from the inside of a polygon. We can just go to a higher space. So instead of P2, we can go to P3, P4, anything we like. Exactly the same formula. So let's say we just do it in the next most interesting case, where I runs from 1 to 4. Okay? You might even think that's the most interesting one for us, because we have data as points in P3. So our z's are 4-dimensional z's. Now, this is actually a perfectly nice object, but we're not interested in it. And the reason is that it's actually not cyclically invariant. So this object was nicely cyclically invariant, but this is not cyclically invariant. And the reason is this stupid minus this twisted cyclic symmetry of positivity. So when I cycle the c's over by 1, there's no minus signs. But because these are 4-dimensional vectors, when I cycle the z's, zn goes to minus, picks up a minus sign. So the cyclic rotation on the z's is not compatible with a cyclic action on the c's. And therefore, this is not a cyclically invariant object. Okay? So the next interesting case then, so it's not a bad object, but it's not cyclically invariant. The next case is when this is 5-dimensional. Okay? Yeah. Right? And so let's talk about that. Okay. Right. Okay. This is a perfectly so this is a nice cyclic space. But it's 4-dimensional, so it's harder to visualize. So, but let's try to understand what are the boundaries of that space. Okay? So everything is simple and linear here. There's nothing. So what are the boundaries of that space? Here, the boundaries were just the lines 1, 2, 2, 3, 3, 4, and so on. And what are the boundaries there? Well, in order to see what the boundaries are, let's look at y and pick any 4 z's that would define a plane that would give a 3-dimensional boundary of this 4-dimensional space. And let's just compute this. I mean, if this is equal to 0, y is on that plane. Right? So we should see in the space spanning over all c's, in this space, does this always have one sign? Is it one sign or the other sign? So that's how we're going to figure out where the boundaries are. We could have done this exercise there as well, but there we know the answer. Here it's a little more interesting. So what is this? This is just C1, 1 A, B, C, D, plus C2, 2 A, B, C, D, plus Cn, N, A, B, C, D. Right? So let me draw A, B, C, D on a circle here. So if these indices are totally random, it's easy to see that this thing doesn't have any fixed sign. For example, the term with 1 there is positive, because C is positive, and this minor is ordered, and everything is fine, so that's positive. But if I have a term in there, it's negative, right? Because I have to reorder them. There it's positive, there it's negative, and so on. So in general, there's no fixed sign for this thing, right? With one important exception. When it's I plus 1, and j plus 1. When it's I plus 1, j plus 1, then here it's positive. Here, because you've got to skip over 2, it's positive. It's positive everywhere. Okay? So we've discovered something remarkable. The faces of this, and this is just a normal polytope, right? The faces of this polytope are the planes I plus 1, j plus 1. Now, you saw from that factorization picture that we had before, this I plus 1, j plus 1 structure is very important. Okay? And here we see that I plus 1, j plus 1 structure emerges directly just as a consequence of positivity. That the boundaries of this thing, the only faces that they have are I plus 1, j plus 1. Okay? Now, actually, let's even go back to the polygon. So here I have n minus 1 variables. covering a two-dimensional space. So they're obviously covering it highly, highly redundantly, right? So it's nice to cover it non-redundantly, to triangulate it in this case, right? So triangulating, of course, we can do it in many ways, but a triangulation corresponds to just setting all but 3 of the c's to be not equal to 0, and that just gives a little triangle in there, right? So in an overly heavy-handed language that will, however, generalize, what we're doing is taking the positive part of G1n, and we're picking two-dimensional cells. The whole space is n minus 1 dimensional, but we're picking two-dimensional cells of the positive part of G1n. And the two-dimensional cells are the building blocks. Okay? If I just take the union of all of them, for example, it would cover the whole thing. But there's there's things that actually triangulate it. For example, there's many of them, but I can have the sum of 1 I plus 1. That triangulates it. Okay, well, you can do the exact analog over here, and the thing that triangulates it, for example, is the sum of 1 I plus 1, jj plus 1. The sum over I and j. Okay? The sum of those simplices triangulates this whole space. Now, if you're familiar with scattering amplitudes for k equals 1, you would be instantly amazed by this formula, because exactly these symbols with a different meaning are the amplitude for k equals 1. Okay? It's precisely the sum of 1 I plus 1, j plus 1. Of course, as in here, there's lots of spurious boundaries. Each one of these triangles, there are things inside, but they cancel nicely in pairs. And here, too, there are spurious boundaries. They cancel nicely in pairs. We have a nice decomposition of the whole thing. All right. Now, actually, up to this point, this object is still, I believe, well known to mathematicians in a very slightly different guise. This is known as a cyclic polytope. And it's what you get if you take the moment curve, 1t, t squared, t cubed, and you just take n points on the moment curve, and you look at the convex hull of those n points, you get something. Okay? You get exactly the same combinatorially. You get exactly the same thing as we have, simply because putting the z's on the moment curve is one way of ensuring that all the minors for the z's are positive. Okay? Because the minors are just Vandermonde determinants, and if they're ordered on the curve, they're all positive. But they don't have to be on the moment curve. All that matters is that all the minors are positive. Okay. So if I actually go back, I said this thing, if this is k and n, what this boundary had to look like was this little jig that I said tells you where you are on this plane. And then it has a k left and a k right. And also this funny intermediate point. That funny intermediate point, by the way, is nothing other than the intersection of these lines I plus 1 and jj plus 1. So that's I. So this is just a little vignette reminder. This is what the amplitude was supposed to do. But I just wanted to say that it turns out that k left plus k right is k minus 1. So that when k equals 1, you're not seeing much of the structure here. When k equals 1, when these guys are 0, these are just 1. Okay? So what we're seeing here is that we have this object. When we go to its boundary are just the planes I plus 1, jj plus 1. But you can be anywhere on that plane. Okay? That's this little factor. Right? So now I have to define what the object is for general k. So this thing I've defined for k equals 1. So what is the object for general k? Well, I just mimic this idea now. Instead of having y live in Pn, we'll have y live in the Grassmannian. So imagine there's k y's, which together span a k plane. And they're a positive combination of the z's. So this is the fundamental space. So alpha runs from 1 to k. I runs from 1 to k plus m in general, just mathematically. M could be anything. But the z's are positive in the sense that all their ordered minors are positive. And the c's are positive in the sense that all of their ordered minors are positive. Okay? So that's the generalization now. Okay? Now, in order for it to be cyclically invariant, m should be even. For the same reason we had talked about before. When I cycle the z's, I pick up a minus sign. When I cycle the c's, I pick up a minus sign. For them to be commensurate, m should be even. Right? Maybe there's something interesting from m odd, but we only care about the case where m is equal to where m is even. The case m equals 2 is even interesting for us. But as we'll see, there's one more layer that only makes sense for m equals 4. So for the whole story, the really minimal structure works for m equals 4. And m equals 4 is what we actually need for the physics. Okay? So m equals 4 is what we need for the physics, and also is really, when we think about it more properly, the minimal structure. Okay? All right, that's it. So this is the space. And just one thing quickly. When n is equal to k plus m, in that case, the z's are just a square matrix. I mean, there's as many z's as i's, so a's as i's. So I can always use a GL transformation to just fix this to the identity. And then the y is just the positive Grassmannian. So in the case where n is equal to k plus m, this is the positive Grassmannian. gk, k plus m. Okay? So I should say the y lives in gk, k plus m. The c is in positive gkn, as I said. And the z is in positive k plus mn. So this is defining some region in gk, k plus 4 in the case that we care about. And that's it. The claim is that those are all actually secretly, not so secretly, all of the tree amplitudes in this theory, okay, are associated with this space. If I say it slightly more precisely, well, let me not say it too much more. Well, so this is a space. There's something else we can talk about, which is a form on gk, k plus m that has logarithmic singularities on the boundaries of that space. Okay. So you can have the space, and you can talk about a form that has logarithmic singularities on the boundary of the space. That form is very familiar in the case of the triangle. In the case of the triangle of the polygon, that form is intimately related to the area of the polygon. Okay. But so anyway, there's a story with actually a form of logarithmic singularities on this space, and the amplitude is roughly that form, is really the form with logarithmic singularities on the boundary of that space. Right.
Do you know the combinatorics of the boundary of this?
No, we don't. Yeah, so that's one. So it obviously generalizes the positive Grassmannian in some way, so there must be some extension of that beautiful combinatorics with affine permutations and all the rest of it, but we don't know what it is. We know what they are. I mean, we know what the singularities. We know what many of the boundaries look like. No, but we don't understand how to. Yeah, that's the most zeroth order question is, what are its boundaries? How do you combinatorially understand the boundaries? What are all the different cell decompositions of it that you can have and so on? Okay. But notice that if you want to find a cell decomposition of this guy, what you have to do is find cells in the positive Grassmannian of dimension, this has dimension k times m, or 4k. So you have to find special 4k dimensional cells of the positive Grassmannian. But now you know why you're putting particular ones together. You take random 4k dimensional cells that are overlapped, they'll do some crappy thing. But the correct 4k dimensional cells will just give you a cell decomposition. And magically, not magically because this is the answer, the guys that give you the cell decomposition are exactly the guys that we had to add up to get the amplitude. Okay? So that's what the amplitude is. The amplitude is triangulating, or cell decomposing this space. Literally cell decomposing this space. Okay? But it is remarkable that this little one-line equation is encoding all the complexities of tree-level scattering amplitudes. This is just tree amplitudes. Now I'll tell you what the story is for all loops. Okay?
So now did you say you have a form on the space?
There's a form on the space with logarithmic singularities, and it's once you know the cell decomposition, the form is trivial. It's just the d log of all the positive coordinates for the form, right? So this is why I said before, if you actually want to do anything, you really need to know everything about the positroid, because you need to know there's nice positive coordinates for all the cells, and once you know which cells you're adding up that gives the cell decomposition, the form is just d log of all the positive coordinates on each cell, and then you add them all up. So that pushes forward or pulls back. I always forget which is which. This natural form on the positive Grassmannian into GK k plus m. It works exactly. I mean, there's probably a lot more to be understood about the structure of that form, just as an invariant thing, independent of its interpretation in this positive way. But what we really understand well, or better than anything, not that well, is this positive space. But if you don't mind, if I can just take 5 minutes, let me just show you. I wanted to show you how this thing does the magic, how it really does. You know, as we go to its boundaries of the space, it really breaks up into two pieces with exactly the data we need, an I plus 1, j plus 1, something intermediate, exactly the thing which, to a physicist, there seems no other way of doing it other than having particles moving around in space-time, and it's nothing other than the boundary structure of this wonderful little space. Okay, so let me just show you how that happens. And let me do it in the simplest case of k equals 2. So when k equals 2, oh, sorry, I should have said something right at the beginning. The argument that we went through here, saying what the boundaries of the space are, goes through exactly the same here. The boundaries of the space are exactly when this k-plane y contains the plane ii plus 1, jj plus 1. It's exactly the same argument, because when I sandwich y here, I get a sum of a bunch of positive minors. All the rest of the argument goes through exactly the same. This ii plus 1, jj plus 1 argument is exactly the same. Okay, so the boundaries of this thing, so we have this k-plane in k plus 4 dimensions, and the boundaries are when it contains the 4-plane ii plus 1, j plus 1. Passes through the 4-plane ii plus 1, jj plus 1. Okay. So now I want to see what does it look like on that boundary when it actually goes to the plane ii plus 1, jj plus 1. And so let's say I've ordered the indices like this. And so now this is a 2-plane in 6 dimensions, let's say. I'm doing g to 6, k equals 2, m equals 4. The fact that it passes through ii plus 1, jj plus 1 means that I can always say that if I think of this 2-plane or a line as a point y1, y2, that y1 lies in this plane, and y2 is anywhere. Okay? So that means that this matrix C is only going to have, let's say the top row only has non-zero entries in ii plus 1, jj plus 1, and zeros everywhere else. But at the moment, we don't know what the bottom entries look like. Okay? All right. Well, it's easy to see that we can't actually have it be 0 everywhere here and there. If it was 0 everywhere here and there, then y2, the second point, would also lie in this plane. And so we've gone too far. We're not just going to just the first boundary. We're making it much more special than that. Okay? So we just want to make sure that it lies in, yeah. So that means that at least some guy in here or there has got to be non-zero. Let's say it's non-zero in here. I can always rescale it to be 1. So that minor is positive. That tells me that x has got to be positive, because that minor needs to be positive. That tells me that y has got to be negative for that minor to be positive. So let me put a minus sign there. That tells me that z has got to be negative. So let me put a minus sign there. Okay, and then similarly, anything else in here should be positive. All these other guys are positive. But you see, I can't have anybody in here. Let's say there's some guy there in W. W would have to be positive by that minor, and would have to be negative by that minor. So if you have anybody in here, it's got to be 0 in here. And vice versa, right? But what is this in here? It's just a sum of a bunch of positive things in the one lower row. So you could have it on one side, you could have it on the other side. That's exactly this picture. Okay, with k equals 0 on one side and k equals 1 on one side, and so on. So in fact, the general case is you can show that if it looks like I plus 1, jj plus 1, that you have to have matrices here with rank such that the sum adds up to everything, and they overlap on a anyway, it all works out exactly as it's supposed to. And the little extra point I plus 1 has to do with these little boundaries here between the fact there's 2 columns here with non-zero guys populating and so on. But when you just study what the boundary looks like, you see it's a positivity that forces it to break up into 2 pieces exactly the way we normally, as physicists would say, amplitudes do. Right. Okay. And that's really, that geometric fact is really what tells you this is an amplitude. Right? I mean, it has all the properties of an amplitude. Okay, so I hope I've given you at least a feeling for what this object is like. And so let me just end without saying very much about it, but saying what the story is for general loop order. So for general loop order, we have to get these L lines in something that looks like P3 as well. What we naturally have here is GK, K plus 4. Okay? So what do we have? We have, we have this K plus 4 dimensional space. We have a K plane, Y. And Y is positive in the way that we said. Right? But this K plane Y has a natural dual, a 4 plane. I'll call it T. So move this K plane in K plus 4 dimensions. Its complement is 4-dimensional. And so what I'm going to imagine now, so the space on which this form lives is K planes in K plus 4 dimensions. And in its 4-dimensional complements, I have L lines, okay, that live in its 4-dimensional complement. Okay? Now, I can label the lines, the first one by 2 points on it, A1, A2 modulo GL2. So that's for the first one. For the second one, and so on. Right? So I don't know what this space is called officially. People tell me it's called a flag manifold or something. But I don't know what the official, if you could tell me what the official word is, that would be helpful. But that's what we have in mind. So we have this K plane. Its complement contains a bunch of lines, L lines, or L2 planes in 4 dimensions. All right, Y is written as C dot Z. I'll suppress indices here. Well, let me just write it. Okay. A, each one of these lines, all these things are just given in terms of, so these are the C's for the Y's. A is given by sum of the Z's. And I'll call this for the loops. So A1 is given for the loop 1, and so on. So these are 2 by n matrices. If I have L loops, I have this. Okay? And the only condition is that if I group all these things in a gigantic matrix, so here's CY, here's C1, CL1, CL2, CLL. So this is K, and each one of these is 2, so this is 2L. Okay? That all the minors of this big matrix are positive. That's it. All the minors that include, all of them have to include CY. So CY is positive, CY, and any number of the C's. Any number of the C's are all positive. All these minors are positive. So is that clear? So I'm telling you how to build. I'm just giving you explicit coordinates for I'm just telling you exactly what part of this space I'm interested in, what the analog of the inside of the polygon is. And it's that y is positive as before. But all of these guys are positive. They're all just positive. There's a GL2 acting on these guys. And the fact that these live in the complement of y is why all the minors have got to include a y. I'm just projecting through y. So projecting through y, all the minors are positive. Okay? So this is a space. There's a form omega, which has logarithmic singularity. So if I call this space P, if I call this space P of n and k and l, there's a form omega with logarithmic singularities on this space. And that form is essentially the amplitude. Okay. So once you have the space, you know the whole thing. So the question of computing the scattering amplitude is completely reduced to finding a cell decomposition of this interesting space. Okay. So that's the promised half blackboard. This is n equals 4 super Yang-Mills. As I said, no path integrals, no gauge symmetry, no Lagrangians, just this. And now, but we've turned it into, now, I haven't had a chance to show you, but you can show it's an actually even simpler argument than the factorization argument, that the second term in the singularities arises as the boundary structure of this thing. Okay? So it really has the singularities that I claimed, including at loop level. And so we just have to now understand this space. Okay? Part of it is intimately connected to the positive Grassmannian. Just is very closely connected to the positive Grassmannian. But actually, you see, even for k equals 0, if you go to loop orders, there's this interesting space. There's a very, very simple space. If you have k equals 0, so forget about k. Now we're just in P3. We just have lines in P3, L lines in P3. And we're just interested in the L lines in P3 such that all the minors are positive. That's it. That's a nice part of the space of L lines in P3. And that's the simplest non-trivial loop amplitudes to any loop order. Okay? That's a somewhat different seeming space in the positive Grassmannian. They're all actually really closely tied to each other. I should say, where does this funny looking structure come from? What would motivate you to think about this? This is, one way of motivating it is that you're actually sort of hiding particles from the Y Grassmannian. Okay? So it's like, just say this very, very quickly, and then I'll end. If you had a big positive matrix, but you have some particles, A, B, C, D, and so on, that you just want to hide, you want to ignore them. The easiest way of ignoring them is just to ignore them. So you can always sort of gauge fix, just to be concrete, you can always gauge fix the matrix to look like this, let's say. Let me put them adjacent to each other. You'll see it doesn't matter in a second. So I just want to ignore them. I just want to chop off that part of the matrix and look at the rest of the data, right? But you see, if I do that, I exactly get something of this form. I get a 2 by n matrix here, a 2 by n matrix here, and some rest here. All of these minors are positive by that positivity, but all these subminors are also positive as well. Okay? Just by dint of this whole thing being positive. So just by ignoring a bunch of particles, you get a structure that makes you look at this kind of, this sort of moduli space. And you can see why you have to go to n equals 4 for it to be meaningful. Because, where should I put them to ignore them? I mean, let's say I just wanted to ignore one particle at a time. Well, it would obviously depend where I put them. If I put one here and one there, I would get plus signs or minus signs as I move them around. There's no natural notion of positivity. When there's 2 at a time, it's like the II plus 1, JJ plus 1 argument. When there's 2 at a time, you can put them anywhere, and it doesn't make any difference. And also, if you have many of them, you obviously have to have an even number of these guys in order for this function of these lines or of these objects, whatever they are, to be symmetric. Because if I say the minors are positive, if these were 1 by n rather than 2 by n matrices, it would depend who I put first. But when they're even dimensional, it doesn't matter. So the first place where you can have something which has a structure with extra data, living in the complement of y is m equals 4, and it's lines. Okay? And that's what corresponds to the real physical problem. All right, so I think I will end it there. But what we need, what we're exploring a lot ourselves, but I think we could need not just help, but I think there's a sort of fascinating structure here. But it's really all aspects. It's understanding the boundary structure. It's understanding the cell decompositions. But the thing which would have the maximum payoff to us in physics is to actually find the cell decomposition of these things. Even for k equals 0, if we could cell decompose this for all L, we would have an explicit expression for the all loop scattering amplitude for n particles in the simplest case. It would be a really remarkable thing. But it's reducing these questions to a cell decomposition problem for this space. So thank you. Sorry for going on so long. Yeah.